So welcome everybody. This is the first meet of the number theory meet series. The series is most likely to have 2 meets. So in the first meet, we will cover the following topics. We'll first begin with the divisibility, which includes GCD, LCM, and some properties of them. You will see that many problems on code forces and code chef and other contest sites uh, contain these GCD property based problems. Then we will move on to modular arithmetic, which is very highly used topic uh, in all the programming questions. You won't see direct questions from these, but every question requires a knowledge of this. Then we will move on to binary exponentiation, and then we will look some theorems which knowledge of which will help you uh, future in future. And then an awesome problem, Fibonacci numbers. So let's get started. Arjo.
Yeah, so first thing that we would like to discuss. So in the meet, the most things that will cover are mostly divisibility and modular arithmetic. So a bit of historical reference, like modular arithmetic was introduced by Gauss, and yeah, so he's kind of the god of number theory. Let's go to the next slide, Amul. Yeah, that's Gauss, and next slide. So let's go into divisibility. Okay, so what do you mean when a number is divisible by another number? So suppose you have a number A and then a number B. So the thing that we actually mean is that A can be represented as BQ plus R for certain numbers A and B, where Q and R are unique and B is less than equal to A. Okay. And similarly, this remainder R will also be less than equal to B and greater than 0, will be less than B and greater than 0. So this is what we mean when we explain divisibility. Okay, so this form is kind of redundant when we learn number theory, when we learn modular arithmetic, but like it's nice to remember so that you can manipulate stuff even while doing modular arithmetic. So next slide. So the first problem that I would like to discuss is finding GCD of two numbers. So suppose you have two numbers A and B, and you have to find the greatest common divisor of both. So how do you proceed? Like, how do you start solving or like approaching the problem? So next slide. So so this is like one of the oldest algorithms devised ever by mankind. So what we try to figure out what is GCD? Like, we try to figure out the greatest common divisor, the greatest number that divides A and B both, right? So the algorithm would be the algorithm that we use is called Euclidean algorithm, and like it was devised by Euclid, and like it's pretty basic, but like once you get a hang of it, you understand like the ingenuity behind the algorithm. Yeah. Next slide. So suppose we have, as I said, suppose we have two numbers, A1 and A and B. Wait, Amul, मैं screen share करता हूँ एक second. मेरे को co-host बना.
You are the co-host, I think. 1 minute.
No.
Okay, perfect.
Look. Yeah. Can you guys see?
Yeah, your screen is visible.
So yeah, so as I said, so I have two numbers A and B. It's pretty simple, but like it's quite elegant. So like we have A. So as I mentioned, like I can always represent A as Q0B plus R0, Q0 plus B, Q0 into B plus R0 by divisibility, by the logic of divisibility. And similarly, now B can be also like B is also a number, and like it can also be expressed as like with respect to R0, because R0 is smaller than B. So it can be represented as Q1 R0 plus a remainder R1. Here R1 will again be smaller than R0. So you can again represent R0 in terms of R1, and we can keep doing the same thing. So ultimately, we can't go to negative numbers, right? So this remainder cannot be negative, right? It has to be 0 at some point. So like by the logic of infinite descent, we will by default attain a finite number k, such that we will have R of k minus 1 equal to a certain divisor into rk plus 0. So like the remainder will be 0, and like rk will divide rk minus 1. Yeah. So now, so what will be the so suppose you have so one second. So suppose you have this rk minus 1 and rk minus 2. So what will be the greatest common divisor between rk minus 1 and rk minus 2? It will be rk, right? So like similarly, rk minus 1 and rk themselves will have the GCD rk, because rk divides both of them. So like so as I said, like the GCD of rk minus 1 and rk will be rk. Similarly, we can take this back again. So like rk minus 2 and rk minus 1 will again be rk. And like that, we can go back directly to GCD of a comma b. So it will still be rk. So you have a kind of a descent over here. Like you can go from a comma b, you can follow the same algorithm, and like you will reach rk. So this should be simple enough, I guess. So what are we basically doing? So what's R0 over here? So what R0 is basically the so what R0 is basically the GCD of like so this GCD is basically B into the remainder that I get by dividing A with B, right? So in modular arithmetic terms, yeah.
How did you get that the GCD of rk minus 1 and rk minus 2 is equal to rk?
Yeah, so okay, so so GCD of R, so how can I write rk minus 2? I can write rk minus 2 is equal to q of something into rk minus 1 plus rk, right?
Yeah.
Yeah, so like so suppose it's okay, so like up now you can divide. Now we know that the GCD, the greatest common divisor that divides rk minus 1 and rk is rk, right?
Yeah.
This holds, right? So now you can use the same thing to prove that you have to divide rk both sides, so that like if this has to be divisible by this, so like the remainder has to be divisible by the GCD of rk minus 2 and rk minus 1, and like and the greatest number that can divide rk is rk itself. So like you'll have rk minus 1 and rk minus 2 ka GCD be rk. So I guess that explains it.
For
And
rk minus 2, rk is a divisor, but how do we know it's the greatest divisor? That's the point. For rk minus 2, for rk minus 1, it's the greatest. That's fine.
for rk minus 2, yeah, so how do you write rk minus 2? You write rk minus 2 is equal to a certain quotient into rk minus 1 plus rk, right?
Yeah.
Yeah. So now you get so now you can use you can use simple proof by contradiction, that if you have a number that is greater than rk and yet divides both of them, then that number will also divide rk, right? But it cannot be greater than rk, right? It has to divide rk as well.
Oh,
Do you get it?
got it. Thank you.
Got it, right? So I think I should explain it once for other people. One second.
Arzo use Jamboard.
Yeah, excellent. Application. No, excellent. You can see this way. Yeah, so what he was saying is basically you have rk minus 2 is equal to certain
Arjun,
some q. Right?
We can't
Yeah,
see it.
we can't see your screen.
you can.
It's stuck to Zoom only.
1 second. You can see now?
Yeah.
Yeah. So you have rk minus 2, and it will be a with a certain q. You have rk minus 1 plus some rk, right? So suppose you have certain c that is greater than rk, and yet divides both of them, right? So if c divides both of them, then c has to also divide rk, right? Because the remainder that I get by dividing rk minus 2 with respect to c is 0. So this side also I must have a 0. However, this gives by default gives me 0 because I am saying c divides both of them. That is my argument. But now c cannot divide rk, right? Because c is greater than rk, and any number that is greater than a certain number cannot divide the number itself. So by contradiction, I get that c has to be less than equal to rk. And from the previous argument that we had, GCD of rk minus 1 comma rk is rk, we by default get that c can be equal to rk, and therefore GCD of rk minus 2 and rk minus 1 is rk. So yeah, so that is kind of the basic argument, and you follow this argument throughout and you get GCD of AB as RK. Okay, so based on this, what I explained right now, you get your algorithm as this, right? That GCD of A comma B is A when B is equal to 0, and when B is not equal to 0, you get GCD of A comma A mod B. So what is A mod B? A mod B is the remainder that you are getting, right? So if you follow the previous thing that we got, so R naught here is the remainder when you when you divide A by B, and similarly R1 is the remainder when you divide R0 with respect B with respect to R0, and similarly it goes on. So this is the algorithm that you get to find the GCD, and the coding up part would be rather quite simple. So you can just input two numbers like int A and int B. And okay, so one thing that you have to make sure in this algorithm is that B is greater than A, right? Because otherwise you cannot divide the smaller number by a greater number. That makes no sense. So you have to check that A is greater than B before starting this algorithm. And then when B is equal to 0, you return A, and you return the GCD of A comma A mod B when basically when B is not equal to 0. So this is the code for finding GCD. And yeah, this comes handy a lot of times when you need to get something done. But also one thing that you have inbuilt in C++ is underscore GCD, if I'm not wrong. Yeah. So that you can use that inbuilt function as well to solve questions related to GCD. Okay. So let's cover some properties of GCD. So often you find like certain insights that you can get through these properties that you can use in further problems. So one very simple thing is that every common divisor of A comma B is a divisor of GCD by default, because GCD is the greatest common divisor. So any divisor by default divide it. Then we have Bezout's identity, which says that GCD of A comma B can be represented in terms of AX plus BY for certain numbers X and Y. And yeah, I'll show a proof of this because this is necessary for the extended Euclidean algorithm, which Amul will further explain. So GCD is also associative and commutative. That should make sense clearly. So basically, you can do GCD of A comma B is equal to GCD of B comma A. So that is what commutativity means, and associativity means GCD of A comma B. So I'll show associativity once. Yeah, so it will be basically GCD of A comma B comma C should be equal to GCD of A comma B comma C. Yeah, so this is what associativity means. So by default you get that. And what else do we have? We have we have another cool identity, which is GCD of A comma LCM of these two things. You get the LCM of the entire thing. And yeah, the associativity thing that I mentioned can be actually expanded into this form. So you can have R numbers and you can take the same thing. So it makes sense. And A also divides the product BC, and then GCD of A comma B is D, then A by D divides C. Yeah, so these are certain basics properties which you can look back. We will share the slides and you can read all of these and try to prove most of them, I guess. Should be fairly easy. This is one of the interesting properties, like you can, this often comes handy, like GCD of A plus B comma B is equal to GCD of A B, and like B ke saath you can multiply anything, that doesn't matter. This is based on the divisibility with respect to GCD. So if you divide with respect to M, where M is a common divisor, how does that reflect overall by getting this GCD out of the division operation? And you have when x and y are relatively prime, you can represent this as this. You can try to prove this as well. It's not very hard. It'll give you quite a good intuition on how to handle primes with respect to this. And yeah, so this is basically from here you can get this, you can deduce this with respect to this. Okay, so this brings us back to Bezout's theorem. Like, how do you get this cool thing that GCD can be expressed as this, and like, how do you make sure that this is the smallest number for which we can do this? Let's try to.
Sir, could you please show the theorem again? I'm not able to read it. You're going a bit, you're scrolling.
Faster. Oh, good. This one. Yeah, so I'll go over it. Like if A and B are non-zero and GCD of A comma B is the smallest, then GCD of A comma B is the smallest number that can be represented in the form AX plus BY. Okay, yeah, AX plus BY. And that is GCD of A comma B is equal to X plus BY for certain integers X comma Y. So this is the main theorem. You can look at it here also, like the thing that you can represent GCD with respect to this, and the fact that GCD will be the smallest number that you can represent in this one. So how can we try to prove this? Like, any idea? Like any insights?
What are X and Y? X and Y, are they real numbers?
X and Y are integers. They're not real numbers. They're real numbers, of course, but like they cannot be fractional. So in number theory, we will only deal with integers and like natural numbers, not with any real numbers. The computational problem related to this is finding the coefficients, like finding X and Y explicitly. But like, how do you prove that this thing will exist? How do you prove for sure that this is true?
How is this possible if they are integers? If GCD of AB is less than A and B.
So you can have X and Y negative, right?
Oh,
they're
okay,
not natural numbers.
Okay, that way.
Yeah. Makes sense, right? So let's try doing this. So we have AX plus BY. Okay, I'll give you like a few minutes to think on this, like if you come up with anything.
We can go backwards, using that
backwards how?
Euclidean, you proved it, right? Like A equals to Q into B plus R naught, and then you again implied it that B equals to Q2 into R naught plus R1. So like we can go backwards and then find it in the terms of X and Y.
Yeah, that is kind of what we will do. So like we'll consider that we have a minimal element D, such that D can be represented as AX plus BY. And then what we'll do is that we'll try to represent A. So we are considering this as the minimal element, right? We are considering that this is by default less than GCD. So what we can do is that we can write A as QD plus R. So like if it has to be lesser than GCD, then by default it has to divide A. Like obviously it will divide A. That's here. So now you have you get this remainder r by dividing a with respect to this smaller number, smaller than this. Similarly, you get a b corresponding b, q2 d plus r2. Yeah. So now what we can do is that I can represent r1 as a of SD. This makes sense, right? So now what I will try to do is, the major idea would be like I'll try to form a certain relation that will help me to get from R to directly what do you call it? From R I can get directly a form by which I can prove the divisibility. Does that make sense? Like I'll try to do that. Q1. I can put D as AX plus BY. So I'll have A minus Q1 AX plus Q1 BY. This will be minus. Yeah, so I have A1 minus Q1 X plus SL minus Q1 BY. So this will be equal to R. Right? Yeah, so I think you maybe take a time to like get what this means. You can all see my screen, right?
Yes, yeah.
So like yeah, so this makes R okay. So let's think about why this can't work. Like why this should not hold. Like why is this a contradiction? So just I mentioned that D is the smallest number that I can represent as this. Now A is
That
equal
is
to
minus infinity, no? Then what do you mean
minus
smallest number?
Smallest natural number. So all
You
the
said they're
D,
integers.
no. T, A, B are natural numbers. X and Y are your integers. Okay. So D, A, B.
Okay.
So when we talk about divisibility, we will not talk about negative numbers. So like we don't have divisor as negative numbers. So when we talk about divisibility amongst numbers, we will talk about natural numbers. But like when we talk with respect to representation, we'll consider this as integers. So that is Bezout's or Bezout's identity. So what I actually did is that I told Key, okay, let's consider that D is lesser than the GCD, lesser than our GCD. So that makes D representable as this. So that further makes A representable as this and B representable as this, right? So from there we get R1 as A minus Q1D, and we can replace D with respect to X plus BY, and that will give us this. So the contradiction that we get is that R is actually R1 is actually of the form AX plus BY, and that should not hold because the smallest number according to us should have been D. Does that make sense? Like R is not 0, so R has to be necessarily 0, which is do you guys get that point?
Yeah.
Like so that makes R1 and R2 0. Like they should be necessarily 0 because I can use the same contradiction to prove that this does not hold. Like R2 also has to be non-zero. So by default I get D as a divisor of of both A and B. Right. Okay, so let me write that clearly. So I'm considering D to be AX plus BY a number. I'm considering that D does not divide A and B, but I end up proving that if D does not divide A and B, then D cannot be the smallest number. So by default, D has to divide both A and B because R1 and R2 has to be 0, because if they are non-zero, they can be represented as this form again, and that will not make D the smallest number. So what we got till here is that D is a divisor of both A and B. That is the takeaway. Now let's think how can we prove that this has to be the GCD, right? So let's consider let's consider the case that we have a certain let us have a certain common divisor of A and B. Let us consider like C to be the common divisor of A and B, like so let's wait, where is my slide? So let's C be our common divisor of A and B. So you have D is equal to A of C something, C I guess x1 plus Cx1x plus by1y. So sorry, D is equal to Cx1x plus Cy1y. So I'm saying that C is basically the common divisor of A and B, and I by default get that C also divides D. So basically what I get that if C is any divisor, common divisor of A and B, then I get that C will divide D, because this thing I can take common, and if so that makes D a multiple of C. So by default C divides D, right? So for what I proved is that for any number C, such that C is a common divisor of A and B, C also divides D. So that makes D the greatest common divisor, because every divisor of A and B must divide D. So that was the first. That was basically the first property that we talked about. Like every common divisor of A and B must be a divisor of GCD. So since C is dividing D for every possible C, we proved that this common divisor D that we talked about, being the smallest number representable as AX plus BY, is actually the GCD. I guess this was a bit of a long proof. So if anyone has any doubt, please tell. Like anything, like if you didn't get any part, I can go through the entire thing again.
No, you are not audible properly.
Hello, am I audible now?
It's kind of better. Yes, you can go ahead and ask your question.
Yeah.
You said that we can express R1 and R2 in the form of AX plus BY. But how we can prove that R1 and R2 are not smaller than D? Like you said that D is the smallest number because we can express R1 and R2 in the form of AX plus BY. But how we can prove that R1 and R2 are not smaller than D?
Yeah, so R1 and R2 are by default smaller than D, because R1 and R2 are the remainders. So what I started with is that I considered that let D be the smallest number that can be represented as AX plus BY. Okay. D be the smallest number that can be represented as AX plus BY. Then I get the contradiction that I will get R1 and R2 also representable as this form, like certain AS plus B T, right? I will get R1 and R2 also of this form. So now R1 and R2 are lesser than D, because they are the remainders I get when I divide A and B respectively with respect to D.
Yeah.
Okay. So that makes R1 and R2 lesser than D, as well as representable as AX plus BY, which I don't want. Which basically I get a contradiction, right? Because I started off saying that D is the smallest number that can be represented of this. So that makes that, what does that imply? That implies that R1 and R2 must be 0. They cannot be non-zero, right?
Okay.
They have to be 0.
Okay, I got it.
Okay, so yeah. So you get it, like they have to be 0. So I get D as a common divisor. Then I prove that every other divisor that exists will also divide D. So D is a common divisor which is divisible, which we can divide by all other common divisors. So that makes D the greatest common divisor. So that is the basic outline.
I got it.
Okay. So let's move on from this. So I won't go to too many proofs, but like, yeah, these are better to keep in mind. I guess the rest you can prove yourself. So yeah, so I proved it kind of, and like, okay, so you can use the previous you can use the previous GCD finding algorithm. You can just use Euler's original algorithm to figure out the coefficients, and like this is kind of the code for the coefficient. I guess Amul, can you explain a bit of the code?
Okay. Let me just explain it through my screen sharing. Okay, let me just share my
Yeah,
screen.
I'll stop sharing.
Okay. So the code was, oh yeah, right. You can see my screen, right? Okay. So like the
Someone write the
problem.
code. Write the code.
क्या write the code in?
कोड एडिटर खोल के लिख दे.
लिखा हुआ है ना code, like
Right.
cool. So like okay. We have a, so the problem is like we have a equation like ax plus by equal to c, and we have to solve it, like okay, like c is basically the GCD. C is basically the GCD of a comma b. Okay, so what if we have to find the value of x comma y, right? So uh so yeah so what if we had something like cx plus y equal to c? The solution of this would be x equal to 1 comma x equal to 1 and y equal to 0, right? So we have to somehow reach this stage. The current thing that we have is a comma b. Now if we just the coefficient of, this is the coefficient of x and this is the coefficient of y. So if we represent if we move from a comma b and try to write it as a comma b comma a mod b, so that will be basically equal to if we just write it that wait a minute, I think let me just explain this after the modular arithmetic part, and this will be better understandable to you all. So let me just start with the modular arithmetic part now, and I will explain this after that. Okay, cool. So the modular arithmetic part, yeah. What is the modular arithmetic? So what is mod operation? N mod m is defined as the remainder of n when we divide it by m. So this can be this is mathematically equivalent to n minus n by m, the floor of n by m star m. You can think of it how, like obviously n by m is the quotient, and you multiply it n by in with the base, and this gives the remainder. So it is equivalent to this. And you will also, whenever you will read proofs, you will also see this triple equal to notation. So what does this notation mean? Is like f corresponds to g mod m, which it means that f and g have the same value when modded with m. Cool. So let's solve a few examples based on mod operations. 5 mod 3 will be 2. Simple. 10 mod 2 is 0. Now what is minus 3 mod 2? Minus 3 mod 2 will be minus 1. Again, it's not important. Minus 1, you can just convert it to you can just add 2 on it and just say that it's 1. Everything you get, you can just add a multiple of m to it, and the answer will be the same. Like minus 1 is equivalent to 1 is equivalent to 3 is equivalent to 5 with respect to mod 2, and 5 mod 3 is minus 1. Also keep in mind that x mod 0 is not defined in C++ because of obvious reason, division by 0. So which won't be which is not defined. So x mod 0 is not defined, and the precedence order of the mod operation is mod has the same precision as division and multiplication, but it has higher precedence than addition and subtraction. So a plus b mod m is not equal to brackets of a plus b mod m. This will be just a plus b mod m, and this will be a plus b whole mod m. So here's the difference. So like yeah, we just found that p is equal to 34k plus 6. We don't write we don't in number 3 we don't like equations like this. We write it as P corresponds to 6 mod 34. So the basic property is A corresponds to A mod M, pretty obvious. Then A corresponds to B and B corresponds to A, also very much obvious. So yeah, if A is the transitive property, if A and B are, if A corresponds to B mod M and B corresponds to C mod M, then obviously A corresponds to C mod M. The addition now, yeah. So when we add two numbers like A plus B mod M, it's also equivalent to A mod M plus B mod M whole mod M. Why? Let's just prove it. So if we can write A as MQ1 plus R1. So when we just do A mod M, we will get R1. And we can write B as MQ2 plus R2. So when we do B mod M, we will get R2. So the LHS part of over here will become R1 plus R2 mod M. And on the other hand, we will have the same thing. A plus B will be MQ1 plus Q2. And when we mod it with him, we'll get R1 plus 2R2, R1 plus R2 mod M. So pretty straightforward property. Let's move ahead. Subtraction. Again, the same thing. Multiplication. Yeah. So here also the basic idea to prove is the same. We will write A as MQ1 plus R1 and B as MQ2 plus R2. We'll multiply both these things. And when we take it as mod, we'll get that A into B mod M is equal to A mod M into B mod M. Like we can apply the mod operation with A also, and the final answer won't change. So when we see that we have an equation which corresponds to addition, multiplication, subtraction, or division, and we have to answer the final result with respect to some mod. We don't have to just compute this whole thing within the bracket once and then mod it with 3. What we can do is, like, we can just go ahead and apply the mod operation anywhere we want. Like literally anywhere you can apply the mod operation and the final answer won't change. Like when we apply mod operation to 152, we get it as 2, and then the final answer becomes, the calculation of answer becomes very easy. Now, what's the advantage of this mod operation? Why do we use it so often? Like we all know that in C++, we might know that in C++, the integer range is at max 128. So if I just multiply two numbers, 1e10 into 1e10, we get 1e20. So how will we represent the final answer? So we can, so that's why in most question you will see that the final answer they ask is with respect to a certain mod, so that it fits the integer range. Yeah. So what about division? We just talked about addition, subtraction, and multiplication. So modular with respect to division is not so simple. So the division is defined as we need to know something about modular multiplicative inverse. So modular multiplicative inverse of A is a number such that we can multiply A into A inverse with respect to mod M will give us 1. So we should also note that the modular inverse does not always exist. Yeah. So A into A inverse should give us M, right? So that's like yeah, that's like this only.
1 second, is there a bracket there or is there no bracket?
Where? Okay.
A times A inverse, is it enclosed in a bracket or is it A times A inverse mod M?
No, it's enclosed in a bracket. A times A inverse mod M is equal to 1. Yeah, A into A inverse is inside a bracket. Okay, cool. So A into A inverse mod M is equal to 1. That's so the value of A inverse is the multiplicative inverse. So yeah, so it is not always defined. Now why is it not always defined? Okay, let me just show you over here. So yeah, so I told you like A times A inverse mod M is equal to 1, right? So we can just write it as A times A inverse plus M star some variable Y should equal to 1. Like these things are equal, right? Because when we just mod the LCM, we get this and we should have 1. So why when will it not be defined? We have RHS as 1, so let GCD of A, sorry, A inverse is a variable, right? It's a variable. So we know A and M. So if GCD of A comma M is not equal to 1, then it will not be defined, because obviously, because we can just separate, let GCD of A comma M be C. So we can write A as C times K1 and M as C times K2. This is K1. So obviously we will get C common, and the equation won't make sense. So for modular inverse to be defined, GCD of A comma M has to be 1. So now how do we find A inverse? There are basically two methods. One is extended Euclidean algorithm, as we already know that so as we already know that it's like solving for A inverse is like solving this equation only. Solving this equation only. So as Arjo explained, we can solve it using extended Euclidean algorithm. Now let me just explain the code for the same. So here is the code for it, like GCD of A comma B. So I have so I need to find AX plus BY is equal to GCD, which is 1 for multiplicative inverse. So I pass the parameters, and now I go from A comma B to finally I had to reach a stage such that so if I have a final equation as Cx plus Y equal to C, that is we are solving for this, Ax plus By equal to C, and finally we want to reach here, that is Cx plus Y equal to C. Then obviously the answer for it will be X equal to 1 and Y equal to 0. Cool. So 1 minute. The original equation is Ax plus By equal to C. Now the variable, we are at A comma B. Now when we represent it as B comma A mod B, we have to reach here, this, which is B comma A by B star B. So if I just represent the parameters of this equation as x1 comma y1, so this will be equal to B x1 plus A minus A by B star y1. This should be equal to C. So if we compare both the equations, Ax plus By equal to C, we can see that if we have a solution for this equation x1 comma y1, we can get the solution for x comma y as by comparing the coefficients of A and B. Okay. By comparing the coefficient. So let me just write the equation again. We have, our equation was this, and now if we have solution for this equation, that is bx plus A minus A by B star B y equal to C, then x1, sorry. So we can get the solution for x and x1 by comparing. So by coefficient of A, the coefficient of A will be x equal to and here the coefficient of A is y1, and y will be equal to the coefficient of B, which will be x1 minus A by B star y1. So this gives us basic equation. So if we are solving for A comma B comma x comma y, we can solve for B comma A mod B comma x1 comma y1, and then again we can just move ahead and ahead, and finally we will reach a stage with 1 comma 0 comma x comma y, which will have a solution as x equal to 1, y equal to 0, and then we will get the solution for backwards, and then we'll finally come back to here. So let me just go over this again. So we wanted to find a solution for ax plus by equal to c. We represent this state as a comma b comma x comma y. So for this, we find the solution for b comma a mod b comma x1 comma y1, and then we go ahead like this more until we reach a stage 1 comma 0 comma x comma y, the solution for which we already know, that is x equal to 1 and y equal to 0, and then we backtrack to the original problem and we get the solution for that. So this is that code only. Like the code is here. Code is that only. Like we have b equal to 0, the original state, and we just find the solution for b comma a mod b comma x1 comma y1, and from that we get the current state's solution. So this is just based on the GCD idea that finally we will reach this stage. Okay, so any doubts in this code? Okay.
While passing the arguments in the function of GCD, you wrote int and ampersand signs. So what does it signify?
Ampersand sign.
Well, can I explain that?
Yeah.
I'll explain. So in C, this is some syntax in C++. So this is passing the, okay, this is C syntax. Maybe. No?
No, this is the syntax for addressing, right? So what you are actually doing here is because so what you are actually
usually when you pass like ints to your function, int a, b, it will create a copy of the variable. But if you put an and, then it will pass it by reference. So if you just did not put the ands, right, then if you call the function and you change x and y in the function, then x and y won't be changed when you return from the function. They will be a local copy. But if you put an and, it's by reference. This is called by copy and by reference. So if you put the and, then if you go into the function and change x and y, then x and y will be actually changed. They won't be a copy. Okay.
Yeah.
This is, if you put an and, it's by reference.
Yeah. So you can just see that x1 and y1 was over here. We passed x1 and y1. But if we didn't put the and over here, x1 and y1 would get no value. Like it will not be defined because it won't be changed. Whenever the function will be called, it will make a copy of it, and the copy, any change we do will be done with the copy. So yeah, so this will not make sense that x1 equal to y1 and y equal to x1 minus y1. This only makes sense because x1 and y1 were changed in the recursive call. In the next
so to avoid overwriting the value of x and y, we are like calling it by reference.
No, not to avoid. We want to the value of x1 and y1, right? Like when
to override it.
Yeah, to overwrite it. Yeah, the purpose of passing bit by reference is to overwrite x1 and the value of x1 and y1 so that we can use it over here. We can use them over here.
Okay, got it.
Yeah, so also Aditya asked a question, won't the iterative solution be faster than this? Well, the iterative by default it avoids recursion, so it will be faster. Also, you can further optimize, like doing like reusing values, you can further optimize the iterative one as well. Yeah, you can do that.
Since you're asking this, if you look at this, the complexity of GCD is log of n. So even if you have very large numbers, the number of iterations, like one number of recursions will be at most, let's say 30. For 30, let's say recursions, writing an iterative solution, which is more harder to write than this recursive solution, is not really much of an improvement.
Yeah,
so
and also I don't
like
know how to write the iterative for this, and I have not seen iterative for Diophantine. This is also known as Diophantine equation. So I don't know like the iterative version.
It will be really hard to write an iterative solution. Recursive is very easy because recursion is usually easy. Since levels are low, iterative solution will be fast, but not really significant. You should not be thinking about that. There will be other factors that will make your code slower than this.
Okay, yeah. So any more doubts here?
Oh, someone asked, would memoization help in this? So no, memoization would not help in this. Memoization helps when you're repeatedly calling, let's say, some state again and again. But here you will call a state only once. So a state is a comma b comma x comma y, let's say. Okay, or even take a comma b. Okay, in memoization, let's say you have factorial. You do memoization there because from 5, no.
Okay, first let me just tell them what is memoization. Memoization is like you reach GCD of a b x y, and then when you once again commit, you store. You don't want to compute the whole thing once again. You just store the value of the function for these particular parameters. So memoization is that thing. Yeah, cool.
Memoization you use sometimes, let's say, maybe to calculate Fibonacci numbers. So you do that f of n is equal to f of n minus 1 plus f of n minus 2. Then you store a value of f of n minus 1 and f of n minus 2 and keep on calculating. But in that case, you're repeatedly calling the same values, same states again and again. That's why memoization is helpful. Here, you will see that one of A and B will decrease. They will keep on decreasing. So you do not reach the same state again and again. So this is why you do not need memoization. Doing memoization unnecessarily is not helpful. You have to identify when you're calling your states repeatedly.
Yeah, so like memoization in general, like we use for problems that involve recursion in the form of a function rather than like a proper f of n is equal to, like you have a recurrent relation completely. But in this case, you have a recursion in the form of the code, but you don't have a proper recurrence relation that you can reuse multiple times. So that is why you can't use it properly. Also, Aditya again asked a question: is Diophantine equation equal to same as Euclid's? No. So what is Diophantine? So what Amul was talking about was a linear Diophantine equation, which is of the form ax plus by is equal to c. So any equation of such form is called Diophantine equation. So like to find out to solve a Diophantine equation computationally, you use the extended GCD algorithm. So like that is what Amul meant actually.
Okay, so let's move ahead. Yeah. Okay, so we just looked at extended Euclidean algorithm for this. Now let's there's also one more theorem, that is Fermat's theorem. Arjo will be explaining that later, and this helps us to find A inverse. Okay, yeah, and Fermat's is also the most used theorem, and you will get to know why we use Fermat a lot and not Euclidean. Simple division. Yeah, so this is a problem for you guys. The problem is like you are given n integers, and you have to output the largest integer such that when n integers, such that the modular. Okay, let me use null. So you have n integers, a1 to an, and you want a1 corresponds to a2, corresponds to a3, up to an with respect to mod of d.
Certain number, yeah.
Yeah,
D.
so you have to find the largest d. So
yeah. So I guess like let them think for 5 minutes or something, and I'll shift. I'll start sharing my screen.
Yeah.
Correspond thing as in?
Like they should have the same remainder when module when applied mod with d. Was
Yeah,
it a
so-
comment question?
Wait, so you can see my screen, right? I'll explain the problem once more. My screen can be seen, right? Yeah, so like you have, as Amul told, you have like n numbers, a1 to an, such that so you have, so the input will be n numbers, and what you have to find out is a certain number d. So what will be the property of d is that d will be the largest number, such that when you divide a1 by d, you get you get a remainder, suppose r, and the same remainder you get when you divide every other number with respect to d. So like every number a of I can be represented as certain q of I with respect to d plus r. So this r will be a constant for all ai, and qi's will be corresponding, but it doesn't matter. So what you have to find is that find a way to prove that. So what you have to find is basically that the largest number d which holds such a property. So that is what you have to output. Any ideas like how to proceed or anything? Like what will be d?
We can write a loop, right, which goes from the minimum of this a1, a2, a3 till an, and then it goes from this to minus minus, and we stop when we encounter the largest number which satisfies this criteria.
So you will move. Suppose an is quite big. Suppose like an is your 10 to the power 9. Suppose. So will you go through like all these numbers? Suppose this a1 is 10 to the power 8 or something, and like big numbers, you get it right. So like will you evaluate from 1 till a of n? Right? Will you evaluate?
No. I'm evaluating from the minimum of these numbers backwards.
Yeah.
Backwards
Your
as in
algorithm
1
is
to,
right. Your algorithm is
Minus
right. But
minus.
yeah, so suppose ai, as I told, suppose ai is bigger than a of 1. Sorry, a of 1. Suppose a of 1 is the minimum number. Suppose I've provided to you in sorted order, for example. Okay. So so without loss of generality, I can write a1 is less than a2 is less than a3. Sorry, less than equal to. That makes more sense. To an. Okay, this is clear. So now what you are telling is that you will move from 1 to, or a of 1 to 1, and like keep on checking these n numbers. So what if this is greater than 10 to the power 6 or something? What if a1 is quite a large number? Like how do you do it then? Like your time limit will be exceeded, right? Like the algorithm is correct, like you will get an answer like that, but is that the best I can do? Like, can I do something easier? Like something that uses the idea of modularity and divisibility. Do you get my problem? Like, do you get why I can't do this?
Yeah, so we can check only the numbers, only the factors of a1 that reduces the algorithm complexity, right?
But you have to further do a prime factorization.
Oh no.
Yeah,
sorry,
but that
that's
thing
wrong.
is also wrong. Like, it is not necessary that d is a factor of.
Yeah,
A1.
that's wrong.
Yeah. Further. Yeah. So any ideas what d can be? Like any candidates for d? Suppose d is a, I don't know, d is a position. Who do you think will hold this position? I just want to find the largest number. Like what comes to mind when I say the largest number? Like, I've talked about so much. Anything like greatest number, largest number, what do you think they can be?
We can do it this way. We can subtract the same number from all of these and then find the GCD.
We can subtract the same number from all of these and then find the GCD of them. Yep. So what you want to do is that you want to find the least number and you subtract it from all of these, and you want to find the GCD of all of these. Yeah.
Exactly.
So yeah, so that's perfect. And Vamshi told ki find the GCD of all corresponding numbers. No, what we have to do is that we have to find GCD of either GCD of all numbers, such that GCD of these numbers, or GCD of the form this, like A or. Okay, so what is the difference between this and this? So here what I am doing, I'm taking the smallest number and subtracting the smallest number from all. And here what I am doing is I am taking I'm taking the first number and then I'm subtracting it from the second, and then I'm again subtracting A2 from A3, and like I'm keeping on doing this thing. Like I'm basically not this. Like I'll just take like intermediate differences. So what is the difference? So let's see what I am actually trying to do over here. Like I'll try to prove it. So suppose A of 1 is x of 1 mod our d, and suppose A of 2 is equivalent to x of 2 mod d. According to the problem, x1 must be equivalent to x2. So what we have, x1 must be equal to x2. Or like you can just write it in terms of modularity, it has to be equivalent. So from this we get this, right? So also another thing, we have A of 2. We can, so what I told, without loss of generality, we can have A1 as the minimum number. So I have A of 2 as A of 1 plus R1. This makes sense, right? So I have A of 1 is equivalent to A of 1 plus R1 mod D. So now I have R1 is equivalent to 0 mod D, right? So yeah, so so what I did here is basically expressed A2 in terms of A1 and figured out that this R1 has to be 0. Now, can I say this for all consecutive numbers? Yeah, I can say this for all consecutive numbers. Like I can take something of the sort, yeah, so I can take any AI and AI plus 1. So I will have AI plus 1 is equivalent to A of I mod D. And then I will have AI plus Ri is equivalent to A of I mod D. So that will give me Ri is equivalent to 0 mod D, right? So what I get is a bunch of differences, but bunch of alternate differences, which is equivalent to 0 mod D. So it will be basically, so now what do I have to, so this further means that the number D has to be the greatest common divisor of all those differences, right? So why is this equivalent to what he said, like subtracting all the smallest number from it? That is because like of the property that a comma a plus b is equivalent to GCD of a comma b. Yeah. So this holds. Since this holds, I get this as the answer. So you can just use a simple code for this. Like you can just do for the GCD, you can take all R1 comma R2, and you can just figure out the GCD. Like if like R2, if R2 is equal to 0, you will return R1. Otherwise you will find GCD. Otherwise you will do like R2 comma R1 mod R2. Yeah. So this is all you have to do, and you solve this problem. So that was kind of basic. Now I'll share my other screen. We'll move on. Any doubts? Yeah, I'll wait a second or two. If you have any doubts, please ask.
Can you check the chat?
Yeah, sure. Yeah, you have, if we have D for 10 and 22, the algorithm will give 10, 12, D4 maximum. Mod 4 of A, you get 12 is 2, 24, 100.
But the you have solved the thing wrong. Like we have n minus 1 numbers. We have to find the GCD of a1 minus a0. So the GCD of a1 minus a0 is like 22 minus 10. So we actually have only one number, that is 12. So the greatest D would be 12, because 10 mod 12 is 12 and 22 mod 12 is 10. Sorry, yeah, 10 mod 12 is 10 and 22 mod 10 is 12 is 10. So the answer will be 12, not 4. So the final solution, let me just repeat the final solution. It's like GCD of a2 minus a1, comma a3 minus a2, comma a4 minus a2, up to an minus 1.
Yeah, so you were not taking a1 comma r1 r2 r3. You were taking only the differences. You were taking r1 r2 r3 up to rn minus 1. So you'll get n minus 1 differences, and then you have to solve it. Does that make it clear? Yeah, don't connect like the two approaches together. Like the first approach was not complete, so it has to be, yeah. So like that, you just complete with the second approach. So let's move on to Fermat's theorem. Okay, so what is Fermat's theorem? So this was a guy called Fermat. He was an amateur mathematician.
Also, before just as you're explaining this, this is a very important theorem. You will use this a lot, so just listen to it very carefully. Like, if you understand the proof, it's better. But in future, you will not obviously use the proof every time. But it's important.
Yeah. So like I'll tell you the proof once. I won't go through too much details like Bezout theorem, because Bezout theorem gave you a proper understanding. But this I don't think you'll remember anyways. So, so what is Fermat's theorem? Fermat's theorem states that if A and P, so what does this mean? What does it mean for two numbers to have a GCD1? That means that the two numbers are co-prime, right? So what if A and P are co-prime? So that in this case, since P is prime, it means that A is not a divisor of P. So what I get is that A to the power P minus 1 will be equivalent to 1 mod P, right? So how do I actually get this? Let's try to I'll prove that in a second, but like first try to understand like what the problem statement is. Like you have two numbers A and P. Again, numbers here mean natural numbers. P is a prime, and A to the power P minus 1 will give you mod 1. So you can represent this number as certain quotient Q into P plus 1. So 1 will be your remainder. Now Amul explained how division works in modular arithmetic. So by dividing, you just get a to the power p minus 2 is equivalent to a to the power minus 1 mod p, because you are just subtracting a power of, you're subtracting one power from both sides, a power from both sides. So that will give you the modular inverse of AI, of A. So yeah, so like we had to find the modular, we had to find A inverse, right? So suppose you have a problem where you have to find the modular inverse of a number modulo a certain prime. So often you in problems, what you see is that you have numbers like 10 to the power 9 plus 7 or 9, 9, 2, 3, 4, whatever. Like those are generally primes. So like whenever you take modulo of those, you can always use Fermat's theorem. Just be sure that A and P are co-prime. That means that A is not a multiple of P, because since P is prime, you cannot have any other numbers of A, if and only if like, yeah, it has to be just a multiple because P is prime.
You said we don't do division, right? We're in mod. How are you dividing here with A?
Yeah, so let me just explain this. So what I said is like modular inverse of A is A into A inverse should give me 1 mod P, correct? So if you just express a to the power p minus 1 as a into a to the power p minus 2. We can express a to the power p minus 1 as a into a to the power p minus 2.
Yeah.
So if we just relate both these equation, a into a inverse corresponds to 1 mod p, and the equation which Fermat gave, a into a to the power p minus 2 is equal to 1 mod p. So we can check that a inverse is equivalent to a to the power p minus 2. Like we
And also
wanted a to the power p minus 2 only. So
yeah, I got it. Also, 1 mod p will be equal to 1, right? If p is greater than 1.
yeah. That's just
So the first eight.
Yeah, that's just a way of writing it. This means that a to the power p minus 1 mod p gives us 1.
If p greater than 1. If p equal to 1, then it is 0.
Yeah, p equal to 1 is not prime. Fermat said that the p has to be prime. Okay, we have not written. Okay, so this is a generalized what Arjo has written over here is generalized Fermat's theorem, that GCD of a comma p is equal to 1. This is a generalized actually the statement is p has to be prime, and a to the power p minus 1 corresponds to 1 mod p. Like for this to hold, p has to be prime.
Yeah, so often when you read literature or anything like problems, you will often find like p used as prime. So I didn't mention it explicitly, but yeah, p is here, of course, means it's prime. Okay, so you have to remember that p is always a prime, and a and p are co-prime, which again means that a is not a multiple. So let's try to prove this, I guess, like a basic proof sketch, not too much details. So suppose I have p minus 1 numbers. Okay, I have a. I have a, I have a, then I have 2a, then I have 3a, then I have p minus 1. Okay, so all these things will give you unique module. So if a is co-prime with respect to p, so if a is not already a multiple of p, then all these things will give you different remainders with respect to p. Okay, so since p does not divide any of these, you can check it, right? P cannot divide any of these, right? Because p neither divides this, p not divides this. So none of these are divisible by p. So they will give you unique divisions with respect to modulo p. So any r a you take, where r belongs to 1 to p minus 1, like yeah, anything r belongs to this thing, will be equivalent to something mod p, such that I'm sorry, this Jamboard works very shit on my laptop. So RA will be equivalent to some number which will be unique. So what do I mean by unique? So like you can't have 2A equivalent to A mod P. Okay, you won't get the same remainder no matter what you do, because all these things have to give you a closed set of all possible remainders that you can get by dividing any number with respect to p. So suppose I have a number n. What are the all possible remainders? What is the set that you get? Like what is the group that it makes? Like that. So it'll give you a z of a. This is how you denote z of n. This denotes basically that the number system is morphed into a circle. So it starts at 0 and ends at n minus 1. So anything greater than n can be represented in these terms. So this is basically the remainder, modular remainder, right? So yeah, so each of these will give you a separate module. It will give you a unique modulo with respect to p. So that gives you that a into 2a into 3a into p minus 1a will be equivalent to 1 into 2 into 3 into p minus 1 mod p. Why is this? Because all these things will give you unique modulo with respect to p, and there are p minus 1 numbers, and p can have at max p minus 1 unique modulos. So these modulos, these numbers have to map in certain way to this. Like there will always be certain ra such that RA mod P will give you 1. Similarly, you will have another number that will give you 2. Similarly, till you will get up to 3. So it's not that A will map to 1 mod P or that 2A will map to 2 mod P, but like they will map, like one number will map to other, but I don't know which one will map. But I can say that all this, if I multiply this together, I'll get it equivalent to 1 into ... up to P minus 1 mod P. So that gives me, this thing is equivalent to P minus 1 factorial, right? So I have 8 P minus 1 factorial. Okay. On this side, I also have P minus 1 factorial because I am multiplying 1, 2, 3, 4, everything. To the power A to the power P minus 1, because A occurs P minus 1 times. So that will give me equivalent to P minus 1 factorial mod P. I guess you all know the factorial thing. So this is equivalent to this, and by the logic that, so now I can always divide this and this, because the P minus 1 factorial is co-prime with respect to P, right? There is no common divisor between P minus 1 factorial and P. So I can always divide it on both sides, and this will give me A to the power P minus 1 is equivalent to 1 mod P. So this is basically Fermat's theorem. So this is the proof that we get from Fermat's theorem. Yeah, so this is the proof. Any doubts? Feel free to ask any doubts, I guess. If not, I'll move on to the next thing. So let's move on, I guess. So one thing that you may ask is that Fermat's, if I have to find A inverse or by using by something that does not involve extended Euclidean algorithm, how do I consider cases where my modulo is not prime? So like, what if P is not a prime? Like, what if I have to find inverse with respect to a number that is not prime? So like with respect to a modulo that is not prime. So what we do is we take Euler's theorem. So rather than this slide, I'll explain what Euler's theorem is here. So suppose you have a number m. I won't go through that thing entirely because it involves what are prime numbers, and like this is a number theoretic function, and I'll explain all of this in the next meet. We'll do that. But I'll give you an overview of what is happening here. So you have a number m, which is, again, just like the previous case, you will have to have it co-prime with respect to A, because if it is not co-prime, then by default A inverse does not exist even. So like I don't have to consider that case at all. So what I have is that Euler generalized Fermat's theorem as this is a function, this phi function. A of phi m is equivalent to 1 mod m. Okay. So what did Fermat say? Fermat said that A of P to the power minus 1 is equivalent to 1 mod P, right? So that I proved. Now Euler generalized it for any number m such that, again, the co-prime thing holds as I told, but m is not a prime. M can be anything, like any number. Just the only condition that I have is GCD of A and m has to be 1. So I'll prove this later, but I'll explain what phi of m is. I'll just say what it means, because otherwise it is incomplete. So phi of m means all numbers less than m, less than or equal less than m, basically, which are co-prime with respect to m. Okay, all natural numbers less than m, which are co-prime with respect to m. So let's think, what if m is equal to a prime number? What if m is a prime number? What do we have for in that case? So like anyone, like what will be a phi of a prime number? So we know that phi is basically number of co-primes less than this number, right? So any idea what phi of p is? I guess I'll say this, like if I have p as a prime number, then phi of p will be all numbers that are less than p, and that involves 1, 2, 3. So like it involves every number up to p minus 1, because all of these are co-prime with respect to p. So I get how many numbers? I get a total of, so I have to count all these, so that by default it becomes p minus 1. So what I have is phi of p is equal to p minus 1. So that gives me a of phi p is equivalent to 1 mod p is a of p minus 1 equivalent to. So what I did is that I proved that Fermat's theorem is basically a special case for Euler's generalization. We'll explain more about what phi p is and how to find how to find phi function later when we talk about number theoretic functions and primes in the next meet, I guess. Also, this is Wilson's theorem. This is also another special theorem, but I don't think you would require it much in CP. At least I have not come across any such problems myself.
Yeah, so
But
we
I
won't be
guess
proving this now.
yeah, so we won't be proving this because you won't get this too much. But like you can look up the proof if you want. We'll post all links later. These are some more theorems that you can look up later, but yeah, we'll post. I guess you can try to prove them yourselves later. Also, you can look up proofs. They're moderately easy. These are some properties relating to modular arithmetic, which I guess you can go through once. Yeah. So
Yeah,
never mind if you can't understand like what these are. Like we will always post, and feel free to ping us also later. Like it's not a problem. So these are some properties. I guess you can look at them later as well. And now Amul will go into binary exponentiation. Amul.
Yeah. Okay. Yeah. So I hope my screen is visible. So we what we have done till now is we just looked at the way to find a inverse is like to find a to the power p minus 1. Like suppose we have an equation 2 into 3 into 1 by 5 mod 7. So how will we be solving this? We will be doing 2 into 3 into 5 inverse mod 7, which is equal to 2 into 3 into 5 to the power 7 minus 1 mod 7. So yeah, so we have to find exponent. So usually the mod thing will usually you will see mod as 1e9 plus 7 on most of the competitive programming side. Why this? Because this is a prime number and this fits, and this makes the result fit in integer range. So integer range is around 1e9 only in C++. So yeah, so there will be a case where you will have to answer the final answer as 1 by x mod this prime number. So for that you will have to find x inverse, which is equal to x to the power mod minus 2. Sorry, mod minus, not mod minus 1, it's mod minus 2 modulo this. So how will you compute this? The basic the naive method is to just multiply x mod minus 2 times using a for loop, but that will take a complexity of 1 in 9. That won't be fast enough and you will get a TLE. So we have binary exponentiation for that. So what we do is we write suppose let's say we want to find 3 to the power 13. We write the 13 in terms of base 2. So that 13 in terms of base 2 is 11012. That is 1 plus 4 plus 8. That is 13. So that gives us, so 3 to the power 13 will be 3 to the power 8 dot 3 to the power 4 dot 3 to the power 1, which is over here. So since so what I say is when we represent 13 as in this form, we can find the final 3 to the power 13 in just log 13 steps. How? So what we will do is, in the first iteration we will keep x as 3 and check if the power that if 13 uh, is 13 has the one set in base 2 in the current iteration. If it has one as set, will take answer as 1 initially, so we will multiply answer with 3, so answer equal to answer star x. So yeah, now we will just find 3 square and check if we want 3 square in the answer. If we want, we will just multiply 3 square with the answer, and then we will find 3 to the power 4. Like at the iteration, we will just do is equal to x into x square. So first we will have 3 to the power 1, then we will have 3 to the power 2, then we will have 3 to the power 4, and then 3 to the power 8. And we will just check if we want that power of 3 in the answer or not. If we want it, we will just multiply it with the answer, and this way we'll get the answer very quickly. So what is the recursion for this? So we will just do is, when we want to find a to the power n, we just check, we find a to the power n by 2 and a to the power, if n is even, we find a to the power n by 2 and just square it. And if n is odd, we will find a to the power n minus 1 by 2 and square it. So every time the power gets halved, so it will take at most log n operations, right? So the code for this is here. Yeah, so we'll just find a to the power b. We will check if b is 0, we'll return the base case as 1. Then we'll find the power of a to the power b by 2. And if b has a one set, basically if we want an extra power, we'll just result into result star a, else we'll just return result into result. So just take a look at this code for a moment, and if you have any doubt, just ask me. So I guess no doubts here. So the overall complexity of this is log b. So if even if b is 1e9, like if we want to find a to the power 1e9, so log 1e9 is around 30. So it will just take 30 iterations, and you will so you can just see the change in complexity from 1e9 to just 30 iterations. Yeah, so this is used very often in competitive programming, like just so yeah, to find modular inverse and just normal binary exponentiation. So now let's talk about Fibonacci numbers. Yeah, okay, before Fibonacci, let me just tell you, like if the final result, like we wanted to find x to the power b mod something, right? So I told you that this value can get very high. So in the code, which is here, so we will just if we wanted to find a to the power b mod something, we will just add a mod over here, like result star a mod this, because like we can just when we want it's like just multiplication, right? So we can just add mod anywhere. So we will just add mod over here, so that the result stays within the limit and it doesn't get blown up to a very large value. So if you wanted to find a to the power b, just add a mod everywhere. Okay, Arjo, now you can just take the Fibonacci thing. हेलो
हेलो, हाँ तू स्क्रीन शेयर करना, मैं बोलता.
Okay. You guys you don't have any doubt with the binary exponentiation, right? Part. Okay, cool. So Fibonacci thing.
Yeah. So okay. I'll screen share my EA also. But okay. So what are Fibonacci numbers? Fibonacci numbers are basically numbers which you get by adding the same. Suppose you start at 1. Okay. So consider 1 as a part of a Fibonacci number, and consider 0 also as a part of a Fibonacci number. So we start with the first two whole numbers. So what you do is that you add the previous two numbers and you get another number, and that forms the next number in the in the Fibonacci sequence. So you get 0, 1, and you add them and you get 1, and then you can add 1 and 2 and you get 2, and then you add 2 and 2 plus 1, you get 3, and like this it keeps going on, right? So any ideas like how you can try to find a Fibonacci number? Wait, I'll share my screen, I guess. Can you see my screen?
Yes, it's visible.
Yeah, I'll look at the chat also. It's guess. Yeah. Yeah, so like that is a very cool thing that you can do. So I would try to form a recursion based on that. I guess that makes sense. So what I will do is that suppose this is Fibonacci, this is the nth Fibonacci that you want to find. So what you'll do is that you'll try to figure out. So like you have a number. Suppose n is less than 1. Okay, so I'll try to form a recursion, right? So what I know is that f of n is equal to f of n minus 1 plus f of n minus 2. So I know this. Yeah, I don't think I need to keep the brackets. Yeah, so this is what I have to do. Great. So let's try to figure out what will happen if n is less than or equal to 1. So as I told you, if n is less than or equal to 1, you'll get return basically n, right? Because if n is 1, you get 1, and if n is 0, you get 0, and both of those are Fibonacci numbers. You return them. And so yeah, so if it is not less than or equal to 1, so what it will be is, suppose it is 3. So how do you do that? Like suppose it's, so how do you get 3? 3 will be basically 2 plus 1, right? So this is how you get 3. So these are the previous two Fibonacci numbers, and you get 3. You just add them. So what you will do is that you will return. So you have to return the value that you get. So you will return fib of n minus, yeah, fib of n minus 1 plus fib of n minus 2. Yeah, so this is what you will return, and this will give you the Fibonacci number for yeah, so this will give you your recursion for their Fibonacci number.
Alapan. For this will just give us 0 every time. For n equal to 1, return 1, and n equal to 0, return 0.
Yeah, so what we can, yeah, n is equal to 1. क्या
n equal to 1 के लिए 1 and n equal to 0 के लिए 0.
Sorry,
because this will just return 0 ना, so ये 0 हो जाएगा.
अरे मैंने गलती से 0 डाल दिया था. It will be n.
Yeah, this is correct.
So yeah, so you don't need to. Yeah, so what you will do is this. You can do what Amul said also, like you can just return, you can just hard code the return values. That will also work. So now you can always do you can always memorize this thing, and you can always keep you can always find you can always keep a array, I guess. You can always keep a big array. I don't know, int dp something. Int dp. You can declare your dp based on like how many elements you have. You can just take a, yeah, so do some max thing, and like you have zeros, and like you can always check, like if this is 1, then return n. Otherwise you can do like, if so you can initialize all of these as 0, and like if dp, like something of the sort. I will write a kind of a pseudocode, I guess. If dp of n is not equal to 0, return dp of n. Otherwise, just return dp of n is equal to this, right? Does this make sense? अच्छा अमूल मेरा स्क्रीन दिखाई दे रहा है ना? Yeah, does this make sense? Like why will this work? Like how am I memorizing and like how am I forming the dp? So this is a recursive dp, right? I can always convert this into a iterative dp. So all I have to do is that I have to write basically so what you do in iterative dp is that you you make some states. So like suppose this is a different Fibonacci function. Yeah, so I'll write iterative over here. I don't have to take any values. I'll consider n already provided. So yeah, so I'm considering that I have already provided some n, or maybe hard coded n. Maybe take n as input. Yeah, so you have f of 0 as 0, as I told, and f of 1 will be 1. Yeah. I'll just write dp so that it makes more understandable that we are actually using dp. So this is again the same thing. This is an array. You initial is the first element of the array. So n is your first Fibonacci, 0th Fibonacci number, and this is like your first Fibonacci number. If that makes sense. So now what you can do is I'll iterate from 2 to n. So since I have the first two base cases, I can always add them and get the next two cases. So all I have to do is that int a is equal to 2, I is less than equal to n, I plus plus. Make sure that you put dp max as something that such that it exceeds n plus 1 because 0 indexing. And you can always do f of I, dp of I is equal to dp of I minus 2 plus dp of I minus 1. So this should make sense why this should work. So the reason this should work is I am doing the exactly same thing. I'm just making it iteratively. So yeah, so that is how it is returning the value with respect to. Yeah, so instead of memorizing, I'm just writing a bottom up dp. Like I am writing a iterative dp, which will just provide me with a faster solution, a little bit faster solution, but like yeah, it doesn't matter that much though. But still, it is way more slower, right? So what is the time complexity of this? Like, what will be the time complexity of this algorithm? It should be O of n, right? Because why is it O of n? Because I have to iterate all the way, right? So that is still I mean, I'm doing a little bit better, but is it that good? That is a question. Like, can I do even better? Like, can I make it even more faster than O of n? Any ideas? Like, I used recursion, which is pretty slow. I can make it faster. I did dynamic programming. Can I make it even faster? Like, I have to make it even faster than O of n. Like, any ideas that you have from what you have learned? Yeah. So Shantanu answered, I can do O of log n. So that is the pretty amazing trick that, I mean, I was pretty excited when I learned this myself. So what do we actually do? Also another cool thing about Fibonacci numbers and like what is this what does this diagram even mean? Is that like you take, these are basically circles, okay? So like initially you start with a circle of radius 1, and then you take both of their like two circles of radius 1 and like construct a bigger line, and you make a kind of a bigger like a part of a circle that has a radius 2, and then you keep on doing that and you get a spiral like this. And interestingly, these Fibonacci numbers arise quite a bit in nature. Like you can find them like a lot of places in nature. It's a meme, of course, but like, yeah. So like you have galaxies which form spirals of Fibonacci form, and hurricanes also, they form spirals in the form of a Fibonacci. Okay, so what Santanu said, yeah. Golden ratio is the eigenvalue of the matrix. Yes. So what you do, yeah. So the golden ratio is found anywhere, I guess, even in human face of human beings. I guess you can find certain ratios that correspond with the golden ratio. But yeah, that's pretty interesting, like how things can be universal in such a way. And yeah, so the idea that I can make it faster is using binary exponentiation, but I consider that in terms of a matrix. Okay, so what I construct here over here is a matrix fn plus 1 and f0 f1. So what is f0 and f1? Like you can just make them parts of an array, like I made. Like what I had is 0 for this and like 1 for this. So I'll start with those base cases, and I will have a matrix that will basically keep extending my Fibonacci numbers. So what I'm doing is that I have a matrix 0 1 1 1 1. So I'll multiply this once and I'll get the Fibonacci number f1 f2. So let's see how it actually works. Like I'll just show the next case, I guess. So suppose you have 0 and 1, and suppose your matrix is 0 1 1 1. You will do so as you learned in class 12, what we'll do is that we'll multiply this with this and like add them. So you'll get 0 into 0 plus 1 into 1, and this is the first number, and the second number will be 1 into 0 plus 1 into 1. And so what you get here is 1 1, right? So that, if you notice, is the next, forms the next Fibonacci series, right? So this is f0, this is f1, this is f2, this is f1. So I can again add this same thing, right? Because what it is effectively doing is that it is adding f2 case, like it is adding fn minus n fn ke saath 0 and adding it with fn minus 1. Like it is adding, and meanwhile I am also getting like yeah, so like this is n minus 1, this is n minus 2, sorry, this is n minus 1, this is n minus 2, and like similarly you will get, like you can add this will be f1 f2, and similarly you can multiply this and you will get like the next two Fibonacci series. So ultimately what we'll get is that we'll keep on doing this n times, and we'll ultimately end up at fn and fn plus 1. So now how do we actually do this? We actually perform a matrix exponentiation thing, which I guess Amul can explain a little bit about, like pros and cons of matrix exponentiation, and like how do you extend from binary exponentiation to matrix exponentiation. But like this is the major idea. Yeah. So Amul.
Yeah. So the basically the problem is we have to find m to the power n and then multiply with the base case. So m to the power n can be easily found out with what we have learned, binary exponentiation. Just the star operation, this time instead of multiplying two integers, we'll multiply two matrices. So if you just do a Google search, you can check that we can just overload the star operation to do matrix multiplication also. So just overload the star operation, and the complexity, the new complexity you will get is the complexity of matrix multiplication into log n. So which is obviously faster when matrix size is not very large. Here the matrix size for this is 2 into that is 4. So the complexity of matrix multiplication will be 4 cube into log of n, which is very less as compared to O of n. So for very large n, we can do this. Like matrix exponentiation is just binary exponentiation, and instead of multiplying integers, we are multiplying matrices. Yeah. Okay. Let's.
Yeah. So yeah. Also, another interesting fact is that if you find a recursion, any recursion of similar forms, like you can always extend these to like k terms, and like instead of Fibonacci, you will get something else. But like you can still perform matrix exponentiation and make it faster than an iterative DP solution. So we'll send you we'll send you guys like a list of problems. Like we have already made a gym kind of thing. So we have added this problem too. So first, I guess you'll try to solve it, and if you can't, we'll organize. Like we'll have a problem solving session also. Like we'll stream us doing all the problems, so you can see like how to code it and like everything. You can get feel free to ask your doubts. You can get a solution there also. Yeah, but like try to implement it first on your own, so that will give you a depth, I guess, like a depth of understanding. Now this is like if you have understood Fibonacci numbers, I guess you can solve these generic problems also. Like since they are related, like I am talking about these problems with respect to Fibonacci numbers, I guess you will already figure out that they are somehow related to Fibonacci numbers, but like the method you use to actually achieve actually reach the solution is more important in this case. So Amul, do you want to discuss the problems?
Yeah, I can discuss the problems. Yeah. So like the first problem is okay. Am I sharing my screen? No.
मेरा screen share हो रहा है, तू screen share कर.
नहीं, मैं डालूंगा later. Okay. Okay. So the first problem is like you have a string of length n, binary string. So basically every number can be a 0, 1 or 0 or 1. So you have to count the number of strings such that the maximum length of continuous subarray that has equal elements is less than equal to 2. So that means you can't have this. You can't have this as a subarray, and at max you can have this as a subarray. So one such example, let for n equal to 5, the example is 1 0 1 1 0. Oh no, this is n equal to 6. So this is a valid string, and then 1 0
could you
1
repeat
1.
the question?
Okay, so you have to count number of strings such that the maximum, such that no subarray is of this kind. Such that no subarray is of this kind, of length n, binary string of length n, such that we don't have this as a subarray. So let me give you an example for n equal to 5. This works. This also works. This works. No, this doesn't work. Oh, this also doesn't work. Sorry. This also doesn't work. Sorry. 1 0 1 0 1. This works. 0 1 1 0 0 1 0 1 1 0. These work. Yeah. Yeah. So we don't have any substring of this kind. Do you guys understand what is substring, right? You guys understand?
No, but what is the question asking? What do we have to count?
Count the number of strings. Number of possible strings.
Number of possible strings. Okay.
Yeah.
Of length n.
Of
which
length
is the
n.
input.
Yeah.
I guess so the solution also, I guess.
Yeah. So let's say we know the solution for f of like for n length for k length array. Sorry. Let's say we know the solution for k length array. So what we can do is, like, if we know the solution for first k letters, we can just append a z. What we can do is let fk denote the solution for k length array such that the last digit is 1. correct, such that the last digit is 1. So what we can do is, now we know that fk is a solution for k. What we can do is we can either append a 0 over here, or we can append a 1, I guess. Wait a minute. Okay, give me a minute. Hmm. Zero gets cancelled out. Number of subarray. K was for k length array, right? Whether I can append a 0 or hmm. Hmm. Wait, I think this is not what I was thinking. The solution doesn't follow right now. Ajo, do you seem to remember the solution for this? Like, I just thought it was Fibonacci for a second, but now the solution doesn't seem Fibonacci to me. I guess let's just skip this problem. I'm very sorry that I thought it was a Fibonacci solution, but thinking it now, I don't think Fibonacci fits here. So we will just look at another problem. I will just I'll post the solution for this question later in on the Discord server. Very sorry for this problem. Let's just move to the another problem as we are already getting late. Yeah. So the new problem. Yeah. So you have a grid of 2 cross. You have to okay. So you have a grid of 2 cross n. You have a grid of 2 cross n. You have to fill the grid with tiles. You have tiles of size 1 cross 2 or 2 cross 1. How many different configurations are there for this particular grid? So for example, let's say one, we can fill the tile like let's say this is for n equal to 3. So you can fill the tile as this and this. So this is one possible configuration. The other possible configuration is this. So for any n, you have to find the configuration. So any solution for this? You get the problem, right? You have a grid of 2 cross n. You have tiles of size 2 cross 1 comma 1 cross 2. You have to fill the grid with the tiles. How many possible configurations are there? Okay, let me just give you 1 or 2 minutes to solve this.
If we have it till f of n minus 1 and f of n minus 2,
Hmm.
can get f of n is equal to f of n minus 1 plus f of n minus 2. This is because if we have till n minus 1, we can add a vertical domino,
Hmm.
and if we have till f of n minus 2, then
Hmm.
we can add two horizontal dominoes.
Hmm. So
We
what
are
is the
not.
recurrence?
It's basically the same as the Fibonacci numbers.
No. If you just think it a little bit more, you will get your method is right, but recursion is slightly wrong.
No, no,
So
उसी को लेना।
नहीं
एक
नहीं
सेकंड
नहीं
से
नहीं.
अबे ड्रॉ कर
So
2
if you have n minus 2, you have two possible configuration. One is this way, and one is this way.
But this will already be
Okay,
considered.
right. This will already be covered.
So
Oh, right.
so what you will do is that so what he said is basically correct. So what you are
Right,
doing
right.
is that you first choose a row based orientation or a column based orientation. Okay. So
Yeah.
so either you influence two columns at once or you influence a single column. So if you influence a single column, you can fill the rest of the columns as you wish, right? So you have f of n minus 1 for that case.
Yeah.
And
So
if you
let
are
me show
influencing
it.
now if you are influencing two columns at once, so now you get a fixed way to enter for the enter a tile for the second row, right? You have to enter the same tile, same horizontal tile. Yeah. So then you fill two columns by default of your by choosing that case, and then the rest you have like n minus 2 columns that you can fill up on your own wish. Yeah. So like for that case you get f of n minus 2, and for the other case you get f of n minus 1. Yeah.
So this is the solution.
And अमूल तू वो contest का solution
Yeah.
सोच रहा था.
So like I will get back to this problem. This seemed to like Fibonacci to me for a second while I thought of it, but
I
when
अच्छा मेरा voice probably cut हो गया था. मैं तेरे को बोल रहा था. I think I kept mute or something. हाँ तो पिछला problem I guess ऐसा कुछ था. I think it was 3 consecutive zeros and 2 consecutive ones नहीं हो सकते or something along that line. नहीं तो मतलब ये प्रॉब्लम का तो वो केस हो जाएगा लाइक टू द पावर n माइनस तेरे को कंसेक्यूटिव्स निकालने हैं वैसा वियर्ड सा.
हाँ, kind of right.
And I guess
Okay,
you have to mention starting at ending also. I'm not
I'll
sure.
post the updated problem on Discord server and we will discuss this problem over there. I'll just show you the gym thing that we have prepared and you can just practice which contains problems based on current topics only. Yeah, so this is the number theory meet gym we have prepared. It's on VJudge. We will share the link. You can just solve practice problems over here. So we have tried to pick problems which have no other prerequisites as only the topics which have been covered in meet uh, are are considered here, except this Chinese remainder thing. You can just try it on your own or just skip it. We didn't cover Chinese remainder in this meet. We might cover it in the next meet or might not.
Yeah, so what we'll do is that once the contest gets over, I'll stream I and Amul will stream all the problems while we solve them.
Yeah.
And like you can we'll explain the solutions, and like I'll explain Chinese remainder theorem while we solve M.
Yeah, so this is open for 10 days. This is just for practice, educational meet, and this is just educational contest. So like solve it at your own pace. There is no hurry, and try to solve all the problems on your own. And you can just always ask for doubt. Ask if you have doubt in any of the problems, or with the just VJust thing. I think for solving this, you will have to create an account on VJust. That's it. Okay, I will thank you for joining in the meet. So that covers. If you have any doubt, you can ask now.
Yeah. Also, Santanu, yeah, we'll send all the resources and everything in another Facebook post we make. So we'll send everything. That is not a problem.
Cool. Then I think we don't have any doubts, or do we? Let me just stop the screen share.
Yeah, also we are sorry for like glitches and everything. Like we prepared the meet in a hurry, so like we couldn't go through everything like we prepared to. And my
Yeah, like
Jamboard
yeah,
was kind
yeah
yeah.
we prepared the meet today itself, so like it was.
So I guess we can. Yeah. So if you have any doubt, like @ me or Amul in program meet को close कर